Hey, hello everyone. This is Austin Kaiser. I'm a flight paramedic and a clinical educator over in California, and this is going to be a brief presentation on the beginner's guide to the oxyhemoglobin dissociation curve, which is always everybody's favorite topic. So hopefully we can make it as painless as possible for you today. So a few things we're going to be looking at. We're going to understand the components of the dissociation curve. We're going to look at alveolar and cellular ventilation and respiration. And then we're going to review the curve and understand what it means to manipulate it and the consequences of manipulating the curve. So what is it? So what it is it is the relationship between saturation, between hemoglobin saturation, or SaO2, and our PO2 in our blood. And it's really important to understand truly what PO2 is when you're looking at it on like an ABG. And what it really is it's how many millimeters of mercury of oxygen is available for our tissues. So we know that as we dump oxygen into our tissues during cellular respiration, we need to have an adequate amount of it in order to give the tissues oxygen. If we don't have an adequate amount of oxygen, then we are not going to give any of it. We're not going to offload any of it to our tissues because we need that gradient. So the reason that we learn the oxyhemoglobin dissociation curve is simply to answer really two questions. And the first question is, in acidosis, why can our SATs be 90% and still make us super happy? And on the flip side of that, why do we hate alkalosis so much? Why do we see that end-tidal CO2 of 20 and that patient is not in a severe acidosis, and we don't like it? In order to understand that, we need to look at the components of what the oxyhemoglobin dissociation curve is. And so the first thing we're going to look at is we're going to look at the components of it. So we're going to look at how do the hemoglobin become saturated with oxygen. So I am sure that all of you know that deoxygenated blood comes from the right side of the heart into the lungs. We get down into those pulmonary capillaries where we have our little red blood cells that are starting to be able to pick up some of those gases. And each one of those red blood cells in that deoxygenated state has millions of deoxyhemoglobin molecules on them. So these little molecules that have those four heme groups that will start to pick up oxygen as they pass by a well-ventilated alveoli. And when this deoxyhemoglobin starts off in this kind of tense state, which is that top little one right there where it's only picked up one little oxygen molecule, as it picks up one, it actually starts to grow its affinity toward oxygen. It's called positive cooperativity. And so we have these little heme groups that will pick up one, and then it'll quickly pick up another, and then another, and then another, until we have full oxygen saturation. It takes just a fraction of a second for this to happen, and then we end up with arterial oxygen concentrations of about 100 millimeters of mercury. So after we pass through the lungs and go back to the heart, the partial pressure of oxygen in our arterial blood is about 100 millimeters of mercury, and the partial pressure of carbon dioxide is about 40. After we travel through the body and we give all of the oxygen that we're going to our tissues and our organs and things like that, we have a partial pressure of oxygen of still about 40 millimeters of mercury on the venous side. That's what returns to our heart. And then we obviously pick up a little bit of CO2 due to all of that cellular respiration and energy production. So we have a pCO2 of about 46 or so. A lot of these numbers are not going to be very important for you to commit to memory, except for really that 40 number. We really want to commit that 40 to memory, what the partial pressure of oxygen is on our venous side. So let's talk about how we get that oxygen into our blood. We need a supply, right? So we get that supply from the atmosphere. atmosphere has a certain pressure that it exerts on the environment, and so we can say that at sea level, the air pressure is about 760 millimeters of mercury. That's one atmosphere. We know from basic school that the concentration of oxygen at room air in a mixture is makes up about 21% of the total mixture. Most of it is nitrogen, and so 21% of 760 is 160, which is kind of weird. So when you think about it, we're breathing in 160 millimeters of mercury into our mouth and nose, but for some reason we're only getting about 100 of it into the arterial oxygen. And that's because when we breathe in through our mouth, all of this gas, all of this fresh gas has to travel through our dead space, right? It's got to travel through all of these non-compressible surfaces inside of our airway, like our trachea and our large bronchi. And so that number starts to decrease as it starts to mix with some of those old gases. And by the time it actually reaches our alveoli, our PO2, or excuse me, the PO2, the concentration of oxygen in the alveoli is only about 104. As all of the deoxygenated blood passes through those alveoli and starts to pick up all of the oxygen, it ends up picking up from 40 up to about 100. The environmental supply of that 104 is pretty much unlimited, and so it would be counterintuitive initially to think that the blood is just going to equal whatever the alveolar concentration of O2 is. When I was first looking at these numbers, I was like, I don't get it. How come it doesn't end up being a PO2 of 80 if the PO2 coming into the lungs is 40 and the PO2 in the alveoli is 104? They should kind of meet in the middle and be about 65, 70, or 80. But because the supply side is essentially unlimited, these two sides, the alveolar side and the pulmonary capillary side, are going to equivalate to about 100 just because the supply is so much more significant. So what does that mean for our patient? We're going to start looking at this oxyhemoglobin curve right here. So we can see on the x-axis we have our PO2, which is the amount of oxygen that's available for our tissues in millimeters of mercury. And on the y-axis we have our oxyhemoglobin, which is the percent saturation. We commonly refer to it as our SaO2. If we look at this top one, we have a typical patient on the normal curve that is sitting at 98%. That corresponds with a PO2 of 100 millimeters of mercury. And remember that 40 number is pretty important. So that means that we're going to dump everything, we're going to offload everything into the tissues except for that last 40 millimeters of mercury, which is going to stay in our venous reserve, and it's going to travel back to the right side of the heart. So that means that there was 60 millimeters of mercury of oxygen available for tissue oxygenation. Now, if we decrease our saturations just a little bit down to 90% saturations, our PO2 is now 65, meaning that we have a substantial decrease in the amount of oxygen availability at the tissue level, down to about 25 millimeters of mercury. Still have some, but not as much as we would like. Now the problem comes right here. When we start to get into this 75% saturation, we can see that it's 75% sats on the normal curve. That drops our PO2 down to about 40. And we know that we are going to keep 40 on the venous reserve side, so that would mean that we would have zero oxygen available for the tissues at a saturation of 75%. Only 25% drop in our sats essentially erases the potential for tissue oxygenation. So hold on, that doesn't make any sense whatsoever, right? I mean, I see patients satting in the 70s, and not all the time, but not infrequently when we get there, and they're not just gonna be dead, right? So we have to have some sort of compensatory mechanism happening in the body that prevents that person from just dying if their saturations get down to 75%. And there's two things that happen. First of all, when the oxygen concentration in the body starts to become low and we enter into that more anaerobic state, that offloading of oxygen is going to go past that 40 number, right? So we're going to have less venous reserve and we're going to be offloading more oxygen into the tissues to sustain life. So that 40 is going to go down. The second thing is that in that anaerobic state, we are going to force that oxyhemoglobin curve to shift to the right. And let's talk about how to shift the curve. So on the left side of the curve, in order to create a leftward shift, there's a few things that we can do. The first thing is we can increase the pH so we can create an alkalotic state. We can also reduce the temperature, so create a hypothermic state. Or if we have somebody who has a reduced 2,3-DPG, diphosphoroglycerate, then we're also going to have a leftward shift in the curve. And we'll talk about what 2,3-DPG is in just a few minutes here. In order to create a rightward shift in the curve, we're going to do essentially the exact opposite. So we're going to decrease pH, so have somebody in an acidotic state. We can have somebody in a hyperthermic state, or we can have somebody with an increased level of 2,3-DPG. Keep in mind on this as well, when I'm saying you can have somebody with an increased, or we can have an increased alkalotic state or a decreased temperature state. This is obviously not something that we are doing to somebody. This is just something that we are having to deal with as a byproduct of whatever's going on inside of their body. All right, so let's break those three things down. We're going to start with temperature. So it's pretty obvious. I mean, if we have an increased activity level in some part of the body, let's say we're doing a leg workout or something like that, then the temperature in those leg muscles is going to increase because of the relative increase in activity. And then our muscles are going to start to look at oxygen with those hungry eyes, and hemoglobin is going to not reluctantly give it up. So or give up oxygen more easily in order to facilitate the increased metabolism inside of those legs because of the increased activity. So increased temperature equals oxygen more easily releasing off of those hemoglobin molecules. The next thing is that if you're working hard, right? So if you have some sort of increased metabolism for some reason, you're going to have an increased glycolysis in the body. So you're going to be breaking glucose down into pyruvate. Pyruvate's going to be entering into that Krebs cycle, which I know that every single person listening to this presentation probably can't stand the Krebs cycle. But when you have the initiation of the Krebs cycle, you have CO2 coming out on the other side. So if you have an increased glycolysis, you're going to have an increased level of CO2. If you have an increased level of CO2, then you're going to have an increased demand for oxygen because you have more hydrogen and everything going through that electron transport chain. And so you need increased oxygen in order to pick up those hydrogen and create water instead of increasing free-floating hydrogen. So increased CO2 levels in the body equals rightward shift. So that way we can offload oxygen more easily into the tissues. The last thing we're going to talk about is that 2,3-DPG, and it's actually pretty simple. You can think of 2,3-DPG as essentially a hammer and chisel, and so if we have a low oxygen state in the body, our red blood cells are going to produce more 2,3-DPG. So low oxygen state, we're going to have an increased production of 2,3-DPG, and all they are is the crowbars for our oxygen. And so if we get that increased production of 2,3-DPG, then they are more readily available to pry oxygen off of those hemoglobin groups and release into our tissues. So 2,3-DPG is a byproduct of a low oxygen state. Or an increased metabolic state where you have an increased need for oxygen. And another thing to really consider when you're talking about 2,3-DPG is the fact that when you give somebody a blood transfusion with packed red blood cells, they don't have this on there. So it's going to take several hours for that diphosphoglycerate to really start being produced again. in the body to assist with the offloading of that O2. So we do need higher concentrations or higher oxygen saturations in somebody who's having a blood transfusion than somebody who does not, because of the fact that they're not going to be offloading as easily as somebody who has a normal amount of DPG. All right, so let's bring it home and go back to that original person, that 75% saturations. We obviously know that that person's not just going to die, right? We're going to enter into this anaerobic state, which is going to increase the production of 2,3-DPG. It's also going to increase the release of hydrogen because we're in that anaerobic state, so it's going to start to create a relative acidosis in that area. So we're going to have an increased release of free hydrogen. And that's going to cause a rightward shift inside of the oxyhemoglobin curve. So now let's look at that 75% saturations, keeping in mind that this rightward shift, that little dotted line on the right, that rightward shift is really mild. We can have some pretty profound rightward shifts if you have a huge acidosis or a huge hyperthermic issue, or you have a ton of CO2 inside of this solution. You're going to have a big rightward shift in that curve, and it's going to be a much more impressive number here. But in just this mild shift at a 75% saturation, it increased our PO2 up to about 55-ish, which previously, remember that it was at 40, and so now we have a PO2 of about 55, which means that we have about 15 millimeters of mercury available for oxygenation, whereas before the shift occurred, we had no oxygen available for the tissues. So rightward curve is very favorable in somebody who has a low oxyhemoglobin or a low percent saturation. All right, so back to those two first questions. The whole reason that we learned the oxyhemoglobin curve is to answer these two questions, right? So why is 90% okay with the acidotic patient? And that is because if you have a rightward shift, because they're acidotic at 90% sats, they still have a PO2 of about 80. So they're still going to be offloading about 40 millimeters of mercury of oxygen into the tissues, whereas before the shift happened, a 90% saturation would yield a PO2 of 60, which would cut the amount of oxygen we have available for the tissues in half, right? So in the acidotic patient, 90% saturation is totally fine, whereas in a completely normal patient, 90% saturation is pretty marginal. We really want to see it higher than about 93%. And the second question is, why do we not like seeing that end-tidal CO2 unless we're doing some sort of compensatory thing for a severe acidosis? And it's because when we have a low end-tidal CO2, meaning we have a low CO2, that is going to create an alkalotic state and a leftward shift inside that oxyhemoglobin curve. And so now if we have somebody who's just hyperventilating for some reason, or we are hyperventilating them on the ventilator, and they've got a saturation at 90%. Now all of a sudden their PO2 is about 55 or 50, and we have only about 10 or 15 millimeters of mercury available for tissue oxygenation, whereas if we would just slow that respiratory rate down a little bit, bring that CO2 back to normal, shift that curve back over into its normal position, we know that a saturation of 90% would give us a much higher PO2. So we don't like alkalosis, and if somebody's in an acidotic state, 90% sats, not so scary. So just remember that normal is best, but if you got to pick one, a right shift is better than a left shift, because a right shift will allow for better release of oxygen into the tissues. And in a very acidotic or hyperthermic patient, a relatively SaO2 is not that scary. So I hope you guys enjoyed this little short video, and hopefully it answered a few questions that you had about the oxyhemoglobin dissociation curve. My name is Austin Kaiser, and if you have any questions, feel free to reach out to me at akaiser@phiaeromedical.com, and we'll see you guys out there.